Welcome to the practical tutorial of bubble sort. So remember the previous lesson we looked at the insertion sort. So here we're going to be looking at how the bubble sort works, and then if there's the time we're going to be looking at how the selection sort works, right? Now the bubble sort checks how the bubble sort works is it checks the adjacency indexes and then compares them. So these are it works. Now given an unsorted array like this, which is 504, and if we are to sort them in an ascending order, so what we do is this. So it compares the first one with the second one, right? So let's work this out. So in the first iteration here, it compares. So is 5 greater than 0? So if 5 is greater than 0, then swap position. So it becomes 0, 5, and then 4. So we have compared this adjacency indexes, and then we'll compare this 5 with the 4, right? This 5 with the 4. So is 5 greater than 4? Now, if this 5 is greater than 4, so it becomes 0, 4, 5. So that is how the bubble sort works. So we just use 3 items to demonstrate this. If we are to use 4 items, the same processes, and then returns back. So if you're doing it ascending order, right? If you're comparing it, you will notice that the largest number in the first iteration, you will notice that the largest number always go to the last index. So if you're using the ascending order, you need to write an instruction to the computer not to compare the last index anymore during the next iteration, right? And that's what we're going to be doing here. So you understand how the bubble sort works. So it's comparing adjacency value. Remember the insertion sort is comparing them. You assume the first one has been sorted and comparing them backward, right? It compares the first one and then it still compares it with the last one. So that is how the insertion sort works. Then this bubble sort is the adjacencies inside. So once it's not sorted, it returns back again to the first one and keep on comparing them, but removing the last one because the largest number is always in the it assumes that the last number has been sorted if you're using the ascending, if you're going through the ascending order. So let's assume that we have another one like this called 8, and we have another one like this called, let me use 2 for instance. So let's sort this one. So let's sort this one. So in the first one here, it compares 5 and 4. It compares 5 and 4. So it compares 5 and 0, sorry. So it swap these ones, it becomes 0, 5, 482, right? Just so in the next one here, it compares these 0 and 4, right? It compares these 5 and 4. Let me just copy this one and paste it here so I won't be confused. So in the next line, it compares 5 and 4. So 5 and 4, it means that 5 is greater. So 4 comes here and 5 goes here, right? So in the next line here, it compares 5 and 8, right? 5 is already greater than, so it goes to the next one here. It compares 8 and 2. So 8 is higher than 2, so 2 comes here and 8 comes here. So that is how it keeps on doing this. So you can see what happens, right? So you can see that the largest number is already sorted in the first place, in the first one. It has been sorted and taken down to the last place. So that is how it keeps on. It goes again down to the first one again and starts comparing them. It goes again down to the first one again, which is 0 and 4, which is okay. 4 and 5, which is okay. Then 5 and 2 is not okay. Then it swaps this. So here becomes what? So here becomes what? 2, and here becomes what? 5, right? So it compares 5 and 8 is okay. So that is how it keeps on doing this. So in the next line, 0 and 4 is okay, but 4 and 2 is not okay. So it swaps them, which becomes what? Is 2, and this is what? 4. So it takes again 4 and 5 is okay, 5 and 8. So it's keeping these ones has been sorted. The 4 is already the largest number, and then instead of like comparing this again, it doesn't compare this, so it only compares this, which becomes what? which becomes what? 0 to this, which all are okay, they're all sorted like this, right? So now let's go to the algorithm. So let's use this small number to demonstrate the algorithm. So we have n equal to, so this n is a variable that holds this list, right? So now we have a for loop for I, right? So this for loop is starting from 0 the length of down to the length of n. With the length of n, we have the 1, 2, 3, which is the total of items here is 3. So this is looping 3 times, right? So this is looping I equal to 0, I equal to 1, and I equal to 2, right? So this is looping 3 times. Now we have an inner loop. We have an inner loop which is for j, with j starting 0. Now down to the length of n, right? Of n minus I minus 1. So I will explain why it's this. Remember how the algorithm works, right? So we want to do it in ascending order, right? So now when I is 0, right? So our j started from 0, right? It started from 0 down to the length. So the length is 3. So 3, when I is 0, is 3 minus I, right? Which I 3 minus 0 is 0, right? So minus 1, which is 2. So J is looping 2 iterations. So it's J is going through 2 times for each of the I, not 3 times, because of for this first one here. Remember the length, which is 3, 1 to 3. 3 minus I at the first one here is 0. So 3 minus 0 is 0, minus 1 is 2. So when I is 0, J equal to 0. So and I is still 0, j is equal to 1. So that is what it means. That is what this means, right? So that is what this means. So when I equal to 1, hmm, when I equal to 1, so it means that the j start from 0, right? So when I equal to 1, it means that the length is 3, right? So 3 minus 1 is 2. 2 minus 1 is 1. Hmm? 3 minus 1 is 2, 2 minus 1 is 1, which means when I equal to 1, j will only go 1 times, which is j equal 0. Now, do you understand how it works now? So when I equal 2 here, now when I equal 2 here, so it means that the j, it means that 3 minus 2, 3 minus 2 is what? 1. Then 1 minus 1 is what? Is 0, right? So when I equal to, nothing will happen to j, so j does nothing. But when I equal to, j does nothing. That's what it means. So because it's 3 minus 2, which is 1, 1 minus 1, which is 0. So it means 0 iterations when I equal to, so j does nothing. So j will only do something when I equal 0 and when I equal 1. So when I equal 0, j goes 2 times, and when I equal 1, j goes just 1 times. So when I equal 2, j does nothing. So that is what this means, right? So now, since we have understood this first step, now we need to apply our conditional if statement. So if we need to get the value of j, right? So if the value of j, remember the value of j, yeah, our j is 0, right? So the value of j in the first one is 5, right? If the value of j is greater than the value of j plus 1, right? If the value of j is greater than the value of j plus 1, so what happens? We need to swap. We need to swap. Let me use swap because we are using the formal way of writing an algorithm. So we need to swap n. We need to swap n j. We need to swap nj with nj plus 1. Then nj plus 1 with nj. So this is a simple bubble sort algorithm, right? So now let's see how this algorithm works. So we have the n equal to 5, 0, 4. So we have understood the first step, which is for I equal to 0 down to the length of n, right? So which we've done this, which I equals 0, I equal 1, I equal 2. Then for j, we have explained this. So now if n of j, so in the first iteration here, when I equal to 0, j equals to 0, so the n of j, so nj will be, so nj here is the 5 because n0. So nj here will be 5, so which is equal to 5. Then it's greater than nj plus 1. So our nj plus 1 will be the next one, which is, remember the nj is n0. So nj plus 1 is like saying n0 plus 1, which is collecting the value in index 1, right? So if this is greater than 0, what happens? So this rule stands, right? So this rule stands. So the new list becomes what? 0, 5, and 4. That's what this we do, right? That's what this we do. So we only do one iteration. Then the second iteration here, when I equals 0 and j equal 1, so it means that nj, right? So nj here will be what? In this one here, nj now, which is 1. So nj here will be 5, right? Which is 5 greater than nj plus 1 here will be 4, right? Nj plus 1 now will be 4, which will now be equal to, since it's greater than, so it will now be 0, 4, and 5 because the rule stands, right? So it comes down to the next one here. You can see that it's already sorted, right? But you still, this operation will still perform because we based on this instruction of the outer loop and inner loop. So this operation will still perform, and this one will not perform because there's no j. So there's no j operation here. So the stuff will return when I equal to 2, it will just return the results, right? So this is the perform here. So when I equal to 1, j equal to 0, right? So when I equal to 1, j equal to 0, so the nj here, right? So we give you, so this is a new list, right? So when j equal to 0, which means it's 0 is greater. So j is greater than, so j plus 1, right? So j plus 1 here is 4. Is 0 greater than 4? No, right? So it still returns what? 0, 4, 5. So now this will be the answer. So when I equal to, there's no j operations here. So the answer will be 045. So that is how the bubble sort works. So even if you add more items here and you follow up these instructions here, you follow up the way I explained this, you see that you see give you the same result. I hope you guys understand the bubble sort. So in the next class, we're going, in the next video lesson, I'm going to be explaining the selection sort. So thank you and God bless you. You can see how it's very simple. You can see how it works. So there's one thing I want to say here is now, if in the best case, remember the time complexity here is O n square, right? You can see the outer loop and the inner loop, right? O n square. So even if this is already sorted, even if assuming that we have 0, 4, 5 here as a list, and we are given the computer to sort this using the bubble sort, right? In the best case scenario, as long as you're writing this algorithm like this, right? In the best case scenario, the worst case scenario, the average case scenario, they all will perform on the O n square. The only way that it can perform on linear time complexity, which is O n, is only when this structure changes. What I mean the structure changes is this, that means you have to have the combination of the linear time, which it needs to check in doing this first loop here, right? As long as you have this two loop, it will still run it. But doing this first loop here, if you check that this has been sorted, then break, do not perform the second loop. That is when you have optimized this bubble sort in order to run on O n in the best case scenario, because this has been sorted, right? Because this has been sorted. So you have optimized the code not to perform the quadratic time. So in the best case scenario is O n only if you optimize it during this first iteration not to perform this second iteration when this has been sorted. Please get that. When this has been sorted. But if you leave it like this, even if you have an n equal to 045, it will still perform, it will still run this first one and run the second one. But if you do a check doing this first one here, that for I down to the length of n, right? Then you start to do a comparison that if this right? If this is greater than this and this is greater than this, right? So if they are all in place, then break without performing this inner loop operation, then you can say that the best case scenario is on linear time complexity. But if the code is like this, then the best case scenario is on O(n) square, the average case on O(n) square, and the worst case is on O(n) square, which is quadratic time complexity. I hope you understand them. So in some of my lessons, I'm going to be teaching you guys optimize and optimize code, how to optimize your code in order to reduce the time complexity to O(n) on the best case scenario, right? On the best case scenario like this, or how to reduce it to a constant time complexity on the best case scenario like this, right? But mind you that if there's a for loop here, it has defeated the purpose of the constant time complexity, right? Because this for loop will go through linearly, to go through one of them linearly. So definitely the best case scenario here should be on linear time complexity if this code is optimized. So I hope you understand that. I hope you understand how bubble sort work. I hope you understand the time complexity, which is the time complexity here using this pseudocode here. This operation here is on O(n) square. So here the best case in this algorithm here, using this algorithm, the best case here is O(n) square. Worst case is big O n square. Average case is big O n square. So let me use big O here, which means order of, right? Order of. So I'll do the same thing for the insertion sort, which I didn't do in the previous lessons. So this is insertion sort. So here the best case, worst case, average case, they are all O(n) square. You based on this algorithm here. But remember it can be optimized, right? Remember that it can be optimized. But these are unoptimized. These are optimized. So an optimized code. So let me just write it here. Let me just write it here. Unoptimized. Unoptimized insertion pseudocode, right? So this will be unoptimized, unoptimized bubble sort pseudocode, right? So I hope you understand the video, right? So on the next video lesson, I'm going to be looking at selection sorts. Thank you and God bless you.